And that equals 1.58 times 10 to the -6 moles per liter. Okay, so that's my concentration of OH negative at equilibrium. So this will be (1.58 times 10 to the -6). 1.58 times 10 to the -6. This will be minus 1.58 times 10 to the -6. Okay. And then my equilibrium is 1.58 times 10 to the -6. 1.58 times 10 to the -6. This is really negligible, so this ends up being 0.15 still at equilibrium. I mean, you can fill in the sig digs if you want, but it's going to be a very, very small number. Okay. All right, so KB equals the concentration of HF times OH negative over F negative. And that's going to end up being 1.58 times 10 to the -6 squared over 0.15. So my KB value ends up being 1.7 times 10 to the -11 when I solve for that. Okay, so there's my KB, my percent ionization. Okay, so percent ionization is the concentration of hydroxide, which is 1.58 times 10 to the -6 over the initial concentration of the fluorine base times 100%. Okay, and that equals 0.0010%. All right, so that's KB percent ionization. Okay. All right, let's do some more complex problems now. Okay, so this question asks, so we're going to actually solve for KB now. I guess we've already done that. But calculate KB for the weak base aqueous ammonia, so NH3AQ. Commonly used in commercial window cleaning solutions. And write the equilibrium equation. Okay, so this is calculate Kb for the weak base ammonia, and then write the equation. So here's what we do. So we have NH3 in water okay, so that's the equation, right? Ammonia is the base, so it's the proton acceptor. Now, from my acid-base chart, Ka equals 5.6 times 10 to the negative 10. Okay, so 5.6 times 10 to the negative 10. So I can solve for the Kb. So Kw equals Ka times Kb. So we can convert. And that's going to equal, right, Kb is going to equal 1.0 times 10 to the negative 14 over 5.6 times 10 to the negative 10. So Kb, when I solve for that, ends up equaling 1.8 times 10 to the negative 5. So I can use this relationship to solve for Kb when I need it. Okay? So be prepared to do that on a test question. So this question is going to put all of this together. This next question I'm going to give you. Okay, so this says find the hydroxide ions, so the OH negative amount concentration POH, pH, and percent reaction of a 1.20 mole per liter solution of baking soda. Okay, so find the hydroxide ion amount concentration, POH, pH, and percent reaction of a 1.20 mole per liter solution of baking soda. So this is a base, so I need to dissociate it first. Now I need to know that baking soda is sodium hydrogen carbonate. So that, if I don't know that, that's something that I should write down. So that's NH plus HCO3 negative. Okay, and that's 1.2 mole per liter, and it's a 1-to-1 mole ratio, so I know my bicarbonate ion's going to be that, or the hydrogen carbonate ion. Okay. Now what I'm going to do is I'm going to make my acid-base ionization reaction. So I have HCO3 negative, right? I'm not going to use the sodium. I'm going to use the HCO3 negative plus H2O makes H2CO3 plus OH negative. And that's what I'm going to use for my ice table. Okay, so I take the hydrogen carbonate ion from the dissociation of the sodium hydrogen carbonate, or the baking soda. And this is 1.2 moles per liter. Right, so that's ICE. Don't worry about that. That's 0, and that's 0. Okay, so what can I do here? I don't have any final ion concentrations, so I'm going to have to use variables for this. Okay. So let's do this. All right, so this is going to end up, right, so that's going to be 1.2 minus X. Okay. So I don't have a pH or a pOH. That's what's different about this. That's plus X. That's plus X. So I have to find the value in the ice table before I can solve for anything else. So I have many more unknowns in this question. All right, so here's my KB. Let's solve. So my KB expression is going to equal H2CO3 times OH negative over HCO3 negative. So that's my KB expression. Okay. Now let's fill these in. So this is going to equal X times X over 1.2 minus X, which equals X squared over 1.2 minus X. So what I'm going to do here is check the 5% rule. Okay. So this is going to be the concentration of the weak base this time over the KB. Okay, we're checking to see if this is greater than 1,000. Okay, so check the 5% rule. Now, I don't have KB. I have to find it. So I have Ka for HCO3 negative on my chart. So the hydrogen carbonate and the carbonic acid equation gives me a Ka. So my Ka, there's a lot to do in this question. So my Ka equals 4.5 times 10 to the negative 7 from the carbonic acid HCO3 negative. Now when I get Kb, right, Kb will be Kw over Ka, and that's going to equal 2.22 times 10 to the negative 8. So that's my Kb. All right, so let's do this. So this is going to be 1.2 over 2.22 times 10 to the negative 8. So I want to know if I can cancel that negative x out. So that's this 5% rule. So when I solve for that, I get a very, very large number, okay? So it is much greater than 1,000. So this is good. So I can get rid of that. And that makes my life a heck of a lot easier. All right, so let's solve for the x value. So my Kb is 2.22 times 10 to the negative 8. And that's going to equal x squared over 1.2. Okay, so when I rearrange to solve, this is going to be 2.67 times 10 to the negative 8. And that equals x squared, and the square root of this is going to equal x. Okay, so that's going to be 1.63 times 10 to the negative 4 equals x. Okay, so the concentration, so what we needed to solve for after doing all this math, I wanted to solve for the concentration of hydroxide. So that equals the concentration of hydroxide. Okay, so check. So 1.63 times 10 to the negative 4 is the hydroxide concentration. POH equals the negative log of 1.63 times 10 to the negative 4. So POH ends up being 3.787. So pH equals 14 minus 3.787, and that equals 10.213. Okay, so check concentration of hydroxide, check POH, check pH. Okay, so pH, POH, and now I need to solve for percent reaction. Okay, so percent reaction is the concentration equals the concentration of hydroxide over the concentration of the weak base times 100%. Okay, so that's going to end up being 1.63 times 10 to the negative 4 over 1.2 times 100%. So I end up with a percent reaction of 0.0136%. All right, and I can check that off now, too. Okay. So dissociate the equation, make your acid-base ionization equation, ice table. And I don't have a Kb, so I have to solve for it using X, 5% rule. Solve for the Kb using the Ka. Once I have the Kb, I can solve for X, and X will be the concentration of hydroxide. And then from there, I can solve for everything else. Okay, that is a big question. And you're converting, right? So you got to be able to go back and forth between Ka and Kb. You could be given Kb and have to convert to Ka. Okay, so page 746, numbers 10 through 13 are some good practice questions. So I think I put that in my previous video. So just a quick reminder here. So I can flip back and forth between Ka and Kb. So just one last example with that, and that'll be the end of the lesson. So this says solid sodium benzoate forms a basic solution. What is the Kb? Okay, so what is the Kb? So I have, right, so Kb equals Kw over Ka. The sodium benzoate value, so my Ka for that, right, so I have a C6H5 COO negative ion. And my Ka equals 6.3 times 10 to the negative 5. And that's in my data booklet, right? So that's going to be 1.0 times 10 to the negative 14 over 6.3 times 10 to the negative 5. And my Kb for sodium benzoate is 1.6 times 10 to the negative 10. All right. So that's the end of this part of the lesson. The next thing I'm going to look at is amphipoteric entities. So you will have, you'll have ions that will have KWs and KAs, KAs and KBs. And that's because they can act as both an acid or a base. So we're going to determine when things will act like acids and when things will act like bases. All right, we will talk later.